Hi friends, welcome back on our YouTube channel. Today, in classical mechanics, we will discuss about Lorenz transformation. We have already know about the Galilean transformation. Now, here Lorenz transformation. So let's start Lorenz transformation. In today's lecture, we will discuss about basic postulates of special theory of relativity, Lorentz transformation, and also about relativity of co-locality and simultaneity. So these three topics we will discuss in our current lecture. So first of all, basic postulates of special theory of relativity. Now, postulates of special theory of relativity. This theory was actually given by Albert Einstein. According to it, the fundamental laws of physics have the same form in all inertial frame. It means if we move from one inertial frame to another inertial frame, then the fundamental laws of physics does not change. It means the laws of physics are identical whether the frame of reference is in rest or moving with constant velocity. Now, second postulate of special theory of relativity says that the velocity of light in free space is constant and its value is about 3 into 10 to the power 8 meter per second. Its value is actually 2.9979245 into 10 to the power 8 meter per second, and it is about 3 into 10 to the power 8 meter per second. So there are two postulates of special theory of relativity. One is this one and another one is this one. The velocity of light in free space is independent of the relative motion of the source and observer. Now, Lorenz transformation. By using the postulates of special theory of relativity, we derive Lorenz transformation equation. Now, Lorenz transformation. On the basis of postulates of special theory of relativity, we require a new transformation in which the speed of light must have the same value in all inertial frame. The transformation must be linear. That is, if the velocity is very much less than in comparison to the velocity of light, then it converts into Galilean transformation. And it should not be based on the absolute time and absolute space, whereas Galilean transformation is based on absolute time, and in that space is not absolute. The set of equations used to transform the space and time coordinates on the postulates of special theory of relativity are known as Lorentz transformation or relativistic space-time transformation. Now, here we have a frame of reference and this is another frame of reference. So we have two frames of reference. One is S and another is S dash. S dash is moving with constant velocity with respect to frame S in positive x direction and the frame S is at rest. So this is our frame of reference S and this one is S dash, and S dash is moving with velocity v with respect to S in positive x direction. So this is the velocity of frame of reference S dash. Now, here we have a point. This is our point P. The position vector of this point P with respect to O is R, and the position vector of same point with respect to O dash is R dash. So, the position vector of point P in frame S is R and the position vector of point P in S dash is R dash. Let the coordinate of point P in frame S are x, y, z and t, and the coordinate of same point P in frame S dash is x dash, y dash, z dash and t dash. Now, this is actually the coordinate of point P in x direction, and this is the coordinate of point P in frame S dash in x direction. Since frame S dash is moving with constant velocity v in x direction, it means after time t, it covers a distance vt. So, O dash is equal to vt. If the measurement made in x direction in frame S dash is proportional to the measurements in frame S, so x dash is directly proportional to x minus vt. It is clear from here that x equal to x dash plus vt. Therefore, x dash equal to x minus vt. And if the measurement made in x direction in frame S dash is proportional to the measurement in frame S, so x dash is directly proportional to x minus vt. Now, if we eliminate this proportionality sign, then equal to sign and also a constant of proportionality, and here we use constant of proportionality gamma. So x dash equal to gamma into x minus vt. Since the laws of physics must have the same form in both frame S and S dash, so the corresponding equation of x in terms of x dash and t dash, since x dash equal to gamma into x minus vt, so x equal to gamma into x dash plus vt dash. So here we replace x by x dash and x dash by x. Also, v is replaced with minus v and t is replaced with t dash. So x dash equal to gamma into x minus vt will be x equal to gamma into x dash plus vt dash. Now, we replace this x dash with gamma into x minus vt. So x equal to gamma into x minus vt plus vt dash. Now, we transfer this gamma from here to here. So x upon gamma equal to gamma x minus gamma vt plus vt dash. Since we want to find the value of t dash, so vt dash is equal to x upon gamma minus gamma x plus gamma vt. Now we divide this whole equation with v. So t dash is equal to x upon gamma v minus gamma x upon v plus gamma t. And it is written here. So t dash equal to x upon gamma v minus gamma x upon v plus gamma t. Now we take common here minus gamma x upon v. So t dash equal to gamma t minus gamma x upon v into 1 minus 1 upon gamma square. So this is the value of t dash. Similarly, t equal to gamma t dash plus gamma x dash upon v into 1 minus 1 upon gamma square. So in this equation, we replace t with t dash with t, v with minus v, and also x with x dash. So we get this equation. Let a light signal is given at the origin when t equal to t dash equal to 0. It means when both frame of reference coincides with each other. So when O and O dash coincides. Now this is the condition. So here O and O dash coincides, and also all the x's coincides with each other. So y coincides with y dash, x coincides with x dash, and z coincides with z dash. It means both frame of reference overlap with each other. Now, in this condition, a light signal is given. So this is our light signal. According to second postulate, the speed of light remains same in all inertial frame. The position of signal as seen from S and S dash after time t. Now, with the passage of time, this light signal starts gradually increasing. So x equal to ct, because c is the velocity of light, and after time t, the light signal travels a distance x equal to ct, because distance equal to velocity into time. Since with the passage of time, light signals grows up, so after time t dash, the light signal travels a distance x dash equal to ct dash. Since x equal to gamma into x dash plus vt dash, now we replace this x with ct and this x dash with ct dash. So ct equal to gamma into ct dash plus vt dash. Now we take t dash common here, so ct equal to gamma t dash and in bracket c plus v. Also x dash equal to gamma into x minus vt. Now we replace this x with ct and this x dash with ct dash, and we get ct dash equal to gamma t into c minus v. Now ct equal to gamma t dash into c plus v, and also ct dash equal to gamma t into c minus v. If we multiply both equations, then c square t dash equal to gamma square t dash and in bracket c square minus v square. Now t dash and t dash will be cancelled out, so c square equal to gamma square into c square minus v square. Now we transfer this c square minus v square from here to here, so gamma square equal to c square upon c square minus v square. And if we take c square common from denominator, then in bracket 1 minus v square minus c square. Now c square and c square will be cancelled out, so gamma square equal to 1 upon 1 minus v square by c square, or gamma equal to 1 upon root of 1 minus v square by c square. Also 1 minus 1 upon gamma square equal to v square by c square. From where we get it? On taking the reciprocal of it, 1 upon gamma square is equal to c square minus v square upon c square. Now this will be equal to 1 minus v square by c square. We transfer 1 upon gamma square from here to here, and this minus v square by c square from here to here. So 1 minus 1 upon gamma square is equal to v square by c square. Since t dash equal to gamma t minus gamma x upon v into 1 minus 1 upon gamma square, now we replace this 1 minus 1 upon gamma square with v square by c square. So this is v square by c square. Now this v and v will be cancelled out. So t dash is equal to gamma t minus gamma x v upon c square. And if we take gamma common from here, then t dash equal to gamma into t minus vx upon c square. So t dash equal to gamma t minus gamma x upon v. We replace this 1 minus 1 upon gamma square by v square by c square. So here we have v square by c square. Now v and v will be cancelled out. So t dash equal to gamma t minus gamma x v upon c square, or this will be equal to gamma into t minus vx upon c square. So this is our t dash. Now gamma is this one. X dash equal to gamma into x minus vt. Now we replace this gamma by 1 upon root of 1 minus v square by c square. So x dash equal to x minus vt upon root of 1 minus v square by c square. Since there is no change in y direction and z direction, so y dash equal to y, z dash equal to z, and since t dash equal to gamma into t minus vx upon c square, now we replace this gamma with 1 upon root of 1 minus v square by c square. So t dash equal to t minus vx upon c square whole upon root of 1 minus v square by c square. These are the Lorenz transformation equations. So here we have a Lorenz transformation from S to S dash. To get the inverse Lorenz transformation from S dash to S, we just replace x with x dash, y with y dash, z with z dash, and t with t dash. Also, x dash y x, y dash with y, z dash with z, and t dash with t. And also, v is replaced with minus v. So this equation will be x equal to x dash plus vt dash upon root of 1 minus v square by c square. This will be y equal to y dash, this is z equal to z dash, and this equation will be t equal to t dash plus vx dash upon c square whole upon root of 1 minus v square by c square. So these are the inverse Lorenz transformation from S dash to S. So here we have inverse Lorenz transformation from S dash to S. Now, important aspect of Lorenz transformation. The measurements of position and time depends on the frame of reference of the observer. If v is very much less than c, then the Lorenz transformation equation reduces to the Galilean transformation equations, because here x dash equal to x minus vt upon root of 1 minus v square by c square, and if v is very much less than c, then this will be equal to 1. So x dash equal to x minus vt, y dash equal to y, z dash equal to z. And if we discuss about t dash, then in Lorenz transformation, t dash equal to t minus vx upon c square whole upon root of 1 minus v square by c square, and v is very much less than c, so this will be equal to 1 and this will be equal to 0. So t dash equal to t, and this is the Galilean transformation equation, because in Galilean transformation equation x dash equal to x minus vt, y dash equal to y, z dash equal to z, and t dash equal to t. So if v is very much less than c, then the Lorenz transformation equation reduces to the Galilean transformation equations. Now, last topic of today's lecture, relativity of co-locality and simultaneity. So first of all, relativity of co-locality. Let there be two events A and B. Since two events are co-local in frame S dash, it means the coordinates of both the events will be same in frame S dash. Let the coordinate of event A in frame S dash are x dash and t1 dash, and of event B x dash and t2 dash. It means space coordinate of both events in frame S dash are same. It shows that both events are co-local in frame S dash, but they happens at different times. Thus, two events are co-local in frame S dash. The inverse Lorenz transformation from frame S dash to S, x equal to x dash plus vt dash upon root of 1 minus v square by c square. Now, x is replaced with x1 and t dash is replaced with t1 dash. So x1 equal to gamma into x dash plus v t1 dash, and for event B, x equal to x2 and t dash is equal to t2 dash. So x2 equal to gamma into x dash plus v t2 dash, because 1 upon root of 1 minus v square by c square is gamma. So by using the inverse Lorenz transformation from frame S dash to S, we get these two coordinates. Now, if we want to find x2 minus x1, then this will be equal to gamma into x dash plus v t2 dash minus x dash plus v t1 dash. Now, x dash and x dash will be cancelled out, and on taking v common here, we get x2 minus x1 equal to gamma v and in bracket t2 dash minus t1 dash. So x2 minus x1 equal to this one. Since t1 dash and t2 dash are not same, so t2 dash minus t1 dash will not be equal to 0. So x2 minus x1 is not equal to 0, or x2 is not equal to x1. Since t2 dash is not equal to t1 dash, and hence x2 is not equal to x1, it means two events which were co-local in frame S dash are not co-local in frame S. Thus, the two events will not be co-local in frame S. Now, relativity of simultaneity. It means two events happen at the same time. Let there be two events A and B. Event A happen at t dash time in frame S dash. So, the coordinate of event A in frame S dash are x1 dash and t dash, and the coordinate of event B in frame S dash are x2 dash and t dash. It means both events happen at the same time in frame S dash. It means both are simultaneous in frame S dash, but both are at different position. Thus, the two events are simultaneous in frame S dash. Now, from the inverse Lorenz transformation from S dash to S, t equal to t dash plus v x dash upon c square whole upon root of 1 minus v square by c square. Now, for event A, t equal to t1 and x dash equal to x1 dash. So, t1 equal to gamma into t dash plus v x1 dash upon c square, because 1 upon root of 1 minus v square by c square is actually gamma. Now, for event B, t equal to t2 and this x dash equal to x2 dash. So, t2 equal to gamma into t dash plus v x2 dash upon c square. Now, t2 minus t1 equal to gamma into t dash plus v x2 dash upon c square minus t dash plus v x1 dash upon c square. Now, t dash and t dash will be cancelled out. We take v by c square common in these two terms. So, t2 minus t1 equal to gamma v upon c square and in bracket x2 dash minus x1 dash. Since x1 dash and x2 dash are not same, so this will be not equal to 0. So, t2 is not equal to t1. Since x2 dash is not equal to x1 dash, so t2 is not equal to t1. It means the two events which were simultaneous in frame S dash will not be simultaneous in frame S. Thus, the two events will not be simultaneous in frame S. Since for co-locality, we took two events which were co-local in frame S dash, and we get x2 minus x1 equal to this one. And for simultaneity, we took two events which were simultaneous in frame S dash, and we got t2 minus t1 equal to gamma v upon c square x2 dash minus x1 dash. Now, if we take two events which are co-local and simultaneous in frame S dash, it means both events are at same position and also both happened at same time. Then this will be 0. So, x2 equal to x1, and this will also be 0. So, t2 equal to t1. It means the events which are co-local and simultaneous in frame S dash will be co-local and simultaneous in frame S. Thus, only co-local and simultaneous events appear co-local and simultaneous in another frame in relative motion. Here we end our session. In today's session, we have discussed about Lorenz transformation, co-locality and simultaneity, and also about basic postulates of a special theory of relativity. Goodbye.